Dear students, today we will discuss the topicity. The Greek word topi means that is place. Okay. We have one example, that is the propane. In this example, when you consider this group, these two groups is called as the homomorphic groups, or these two groups. Okay, these two groups are also called as the homomorphic groups. Homomorphic atoms. When we isolate these atoms, okay, when we isolate hydrogen, these groups superimposable to each other. And also identical, these are the identical and also superimposable to each other. Okay, such groups is called as the homomorphic groups. Again, CH3 and CH3 are again identical ones, attach same carbons, and when we isolate CH3 is a group is same as a second CH3 group. Therefore, these are the superimposable groups and the same one, identical one. These groups is called as the homomorphic groups. In a topicity, we will discuss the geometric relationship and stereochemical, geometric as well as stereochemical relationship between these homomorphic groups. Okay. Now we will discuss the regarding with these homomorphic groups. Related to the homomorphic groups, we have three terms, that is which arises from homomorphic groups, that is the homotopic ligands groups or homotopic relationships. Then second one is the distereotopic relationship. Third one is the enantiotopic relationship. Okay, enantiotopic phases, homotopic phases, distereotopic phases, or homotopic ligands, distereotopic ligands, or enantiotopic ligands. Such things we will discuss further. Now we will discuss first the homotopic ligands. Okay, which ligands is called as the homotopic ligands? Also we will discuss in same discussion, that is the homotopic phases. If suppose we have an example, okay, if suppose like that example is there, when you replaces HA or HB with other groups, that is, if suppose we use it's one of the isotopes, that's a deuterium. When you replaces HA with the deuterium or HB with the deuterium, you will obtain okay, these two compounds are same compounds. Okay, therefore when you replaces these two homomorphic, okay, these are the homomorphic groups, replaces by it's one of the isotopes or any group, it will use the same compounds. Okay, these two compounds are the same compound, okay, not different compound is there. Okay, therefore such homomorphic groups, after replacing of it by side by side replacing by other group or other isotopes, it will give the same product are same chemical bases, that is called as the homotopic ligands or homotopic groups or homotopic atoms. Okay, in this case, that is hydrogens are the homotopic atoms. Okay, that these are the actually homomorphic groups or atoms. Okay, homomorphic group means what? Which are the, when isolate, it looks like the same, which are superimposable mirror images to each other. Therefore, these are homomorphic ligands. And when homomorphic ligands is considered as a homotopic ligands, when by replacing of these two groups will give same chemical basis, is called as the homotopic ligands. Okay, to find out the homotopic ligands or homotopic, the molecule has the homotopic faces or the ligand is the homotopic ligand. We will find out this by using two criteria, that is, one is the addition or first is the addition substitution criteria, and second one is the symmetric criteria. Okay, these two types, by using these two types criterion, we will find out whether your atoms or elements or groups are homotopic ligands or faces are the homotopic faces. Okay, these two criteria, first is the substitution or addition criteria, and second one is the symmetry criteria. Okay, we have one previously that example. Okay, by substitution HA or HB. Okay, by substitution HA or HB with one of these isotopes will give the same chemical basis. Okay, that is under the substitution criteria. When you replaces HA with deuterium or you replaces HB with the deuterium, it will give the same chemical basis, same product. Therefore, by using this criteria or substitution criteria, we can predict that these two atoms is the homotopic ligands or homotopic groups or homotopic atoms. Okay, these two atoms are the homotopic atoms. Okay, another example, if we have the formaldehyde is there, HA and HB, and when it replaces with HA with chlorine or HB with the chlorine, okay, that is substitution. We have substitute HA or HB with other atoms or groups. Okay, these two compounds is one and the same compounds and one and the same chemical basis. Therefore, these two ligands is called as the homotopic ligands. Okay, after replacing of these, one of the atoms will by any group. Okay, in this case we replaces HA with chlorine or HB with the chlorine, we will obtain the same basis. Okay, then if you replaces HA or HB, we will obtain the same chemical basis. Therefore, these two groups are the homotopic groups or homotopic atoms. If suppose we have another example, tartaric acid. Okay, tartaric acid, if suppose we have like that, okay, HA, HB, OH, OH, COOH and the COH. Okay, 2R and 3R, 2R, 3R tartaric acid. Okay, that compound is the 2R and the 3R tartaric acid. Okay, it's not necessary your groups is attached to the same carbon atoms, that is considered as homotopic ligands or the diastereotopic ligands or anisotopic ligand. Okay, it may be these ligands is attached to the different carbon is also. In this case, when you replaces with HA with deuterium or HB with the deuterium, you will obtain the same compound. Okay, if in first case we will replaces HA with the deuterium. Okay, HA we have deuterium is there, OH and then OH HA is the HB is the same. And secondly, you replace this HB with the deuterium, okay, one of its isotopes. Okay, you replace as HA or HB, you will obtain the same compounds. Okay, when you rotate these 180 degree, okay, you rotate 180 degree, your deuterium will become at that position and HB will come at that position at same. Okay, this same compound is obtained from this when you rotate, and we know that when in a such projection, when you rotated the 180 degree rotation of molecule, you will obtain the same configuration molecule. Okay, if you rotate, you will obtain the D is at that position, or if you rotate 180 degree, you will obtain the like that molecule. You rotate, D will go at the left hand side, and one and the same you obtain. Okay, these two compounds are the one and the same compounds, and therefore by replacing of HA or HB with the deuterium, you will obtain the same type of chemical species, same type of the compound. Therefore HA and the HB are homotopic ligands or homotopic atoms. Okay, like that way we have another some examples. If you look such examples, okay, these are the by substitution we will find out the these are the homotopic ligands. Okay, we have some example is there. Okay, this HA, HB and the HC. Okay, these three groups or atoms is homotopic ligands, or if you consider the toluene is there, HA, HB and the HC. Okay, these three hydrogens are the homotopic hydrogens. After replacing of one of them, if you replace the chlorine or deuterium 1, 2, 3, you will obtain the same compounds. Okay, when you are replacing this HA, HB and HC, you will obtain the same compounds. Therefore these hydrogens, okay, after substitution you will obtain same compounds. Therefore these groups are the homotopic ligands. Okay, in homotopic when you replaces the groups, you will obtain not stereogenic center. Remember that in homotopic ligands or homotopic bases, no stereogenic center is the produced. One of the thing is you have to remember that no, in such replacement or in such substitution, no stereogenic center is produced or chiral center is produced. Okay, homotopic phases means if suppose we have the formaldehyde is there and you add the RMGX, okay, that is a Grignard reagent. When you add, and when you add the Grignard reagent, you will obtain these two compounds is not okay. This center is not stereogenic center. When you add the RMGX to the this electrophilic carbon atom, okay, when you add this to this, you will OH is produces and the iron OH is produces. These two compounds, these two chemical species is same one. Therefore, the addition of these two groups, you will not obtain the stereogenic center, chiral center, but these two compounds are the same compounds. Firstly you will opt from top face, and secondly you will obtain the back face. Okay, top face or below face, back face. Two phases is possible, but both these phases are the whether you add from the top phases or whether you from the bottom phase. Okay, that is the bottom phase or the top phase. When you add from the bottom phase also and the top phase, you will obtain the same product. Okay, therefore when you obtain the same product with the phases, if you changes the phases, addition phases, first top phases and the bottom phases, you will obtain the same compound. Therefore the such phases is the homotopic phases. Another example is there. Okay, such type of compound is there. per acid is added. Okay, if you know that when double bond is there and when you add the per, okay, that cis compound is there, when you add the okay, it gives the when you these two equal parties obtained. If you rotated it, therefore it is a meso compound. Okay, when meso compound is there, meso compound means the compound is the same. Okay, when you add per acid to this compound, you obtain the epoxide, and one and the same. There is a same compound is obtained because meso compound is obtained. Two equal parties there, meso compound is obtained, and therefore. When you add from this top phase or you add from the bottom phase, you will obtain the meso compound. Therefore meso compound is obtained. It means what? There is no differential phases is there. At any phases, from any phases you add the per acid, you will obtain the meso compound. Therefore these two phases are the homotopic phases. Okay, that is called as the homotopic. Nothing is changed, no product is changed. It means the from by addition of the reagent from any phase, top phase or bottom phase, no product is the same obtained from when you add the reagent from the top phase or when you add the reagent from the bottom phase. That is called as the our homotopic ligand. So the second criteria is the symmetry criteria. Okay, when your ligands is exchangeable by CN axis of symmetry, your groups get exchangeable, then that is called as the homotopic ligand. Okay, for example, we have such example is the malonic acid is there. Okay, such as the malonic acid is there. When you rotate this molecule in C2 axis of symmetry, okay, there is a C2 axis of symmetry. Therefore, that ligands is considered as the homotopic ligands. Okay, another example is there. Okay, like that example is there. Okay, when you rotate it C2 axis. Okay, C2 axis, if it indicates that there is a C2 axis, therefore these two ligand is exchangeable. When you rotate these molecule, these two are exchangeable. HA gets HB and HA will be converted to HB when you rotate the C2 axis. Therefore, when there is a C2 axis of or CN axis of symmetry is there, your groups get exchanged with C2 axis of symmetry or CN axis of symmetry. That is considered, these groups should consider as the our homotopic ligands. Okay, another example is okay, like that CH3. Okay, cis compound is there. There is C2 axis of symmetry. Okay, therefore these are the homotopic phases. Okay, that phases, both phases are the homotopic. Okay, C2 axis of symmetry is there. Therefore these phases are the homotopic phases. Okay, if suppose like that example is there, formaldehyde is there, HB and when you rotate this with C2 axis of symmetry, there is C2 axis of symmetry, you will obtain, there is exchangeable HA and HB will be there, and therefore this for formaldehyde this phases is the homotopic phases. Okay, therefore by using the substitution criteria or by using the symmetry criteria, you can predict your ligands are homotopic ligands or the phases is a homotopic phases. Okay, like that way we can predict topicity in homotopic groups. I hope you will get all these ideas. Thank you very much.